Hello all, welcome back to the last part of video lecture series of 8. Now we are going to do the hands-on for Granger causality test. So first we will consider this air quality data set. Say this comes with the basic datasets package, and in the air it is, if you look into the description of the dataset, it's New York air quality measurements. So daily air quality measurements in New York between May and September of 1973. So it's a data frame. It has 153 observations on 6 variables: ozone, solar, wind, temperature, month and day. Now we are only focusing on temperature and ozone, but you can try with the other variable as well. So the first thing we are going to plot is temperature data set. That's how temperature data set has. This is the ozone data set. As we have seen, looks like there are some missing values are also there in the ozone time series. So the first thing we are running here is from the LM test. The first model that we are trying to fit is the Granger test, where ozone is a function of temperature and with only lag 1. And if we run this, and data is for air quality, if we run this, the p-value, this is the if test run. So the model 1 is ozone with lag 1 ozone and lag 1 temperature. And then the second model is only the null model, and then it did a test whether the lag model has effect or not, and then it says that okay, the null model is not right, so that means temperature does have an effect on the ozone. Similarly, we run the second model, and in this, ozone again is a function of temperature, but now we are going up to the second order of the Granger causal test model. It's essentially an autoregressive model. And p-value is still small. So we can say that temperature does have effect on ozone. So in order to understand a little bit more how this whole thing is working, so we will take the air quality data. N is the number of samples. First, what we are now, if you look into let us look into the air data. So that's how the data looks like. Okay, that's how the ozone, solar.r, radiation, wind, solar.r stands for radiation, wind, temperature, month and day. Now there are some NA observations are available, so it is always a bit difficult how you do this imputation, but for the time being we are not handling the missing data. We are only going to use the data which is fully available to us, but for the time being, so we suppose we want to fit the first model. We create the lag data set. Okay, so here we have created the lag. So 41 was here, we just created lag 36, just brought it down by 1. Then we created the lag 2 variable. So now you have the lag 2 variables have been created. Okay. Then similarly we create the temperature lag 1 and temperature lag 2 variables. So temperature lag 1, temperature lag 2 variable have been created. Now if you fit the model with ozone lag 1 and temperature lag 1, okay, ozone lag 1 and temperature lag 1, and similarly M1, say for null I will use 0, but just copy this entire thing, and but instead of temperature lag 1 I am dropping the temperature lag 1, so I am just saying the ozone is only function of its own. Okay, now you see ANOVA. If you just run ANOVA between M1 0 versus M1, okay, you can see that it is the F test reject the null hypothesis, and it says that the lag 1 temperature does have effect on ozone. So you can do the Granger Causal test in this way as well. Similarly, this is M2, this test with the 2 lag, and then I can define the model with null model here, but only with the lag ozone, not with the temperature. I am dropping the temperature, and then we run the ANOVA M test or F test 2 comma M2 0, okay, and you can see you can reject the F test, so lag 2 have effect on the ozone. Now if I compute the AIC of model 1 and model 2, clearly the model 1 has a more AIC than the model 2. The model 2 has the lower AIC, so we can we would prefer model 2 over the model 1. Similarly, you can go for the third variable, third lag. We have to create a lag here, so we can always create these lags. First we have to create these lags, so maybe lag 3, 2, 4, 3. So we have to create these lags for ozone, and then now we have to create these lags for temperature, third lag, yes, 3, and then what we need is a model for third lag and ozone plus 3 and plus 3, and okay, and the 3 not null, we just ozone, it will be only function of ozone, and then we will see if it is still effective. But now when we are doing third lag, we are adding third lag, it's not effective anymore. But can we choose M3? What is the AIC of model, third model? Now if you interestingly, if you see what is happening, you see what is happening here, the AIC is constantly dropping, whereas model that means third model is probably better than the first and second model. However, what we are seeing that third model, the lag does not have any effect, so that means we cannot really use, we can't say that third lag has any effect on the 3 lag model of Granger Causal model does any affect any of temperature, has no effect on the ozone. So that means as we are put more and more lags, so naturally what is happening, the model complexity increases and it's going to higher and higher dimension. As model complexity increases, it is doing some overfitting because my AIC is constantly going down, but we know, but most likely it is effectively losing its interpretability, and that's why probably it's not running, it's not giving any effect. But though we know that lag 1 and lag 2 does have an effect. So you can see that very high M3 in case of third model, except the lag 1 model does not have any effect, whereas M2, if you see M2, lag 1 temperature does have an effect. We see it does have an effect, whereas the lag 2 does not have an effect. Also, if you look into the standard error in third model is 0.577, whereas in the second model for lag 1 is 0.50. So that means standard error is increasing. So there is a high possibility that a multicollinearity also creeping in. Because of the multicollinearity, these lags are not anymore effective because their standard error is going up because of the multicollinearity. So you have to be very careful about how you do the interpretation of these statistical inference, and these you have to be very careful about these statistical inferences particularly when you are adding more and more features. Just because every time you are increasing lag, that means your model is getting complex, your complexity of your model is increasing, it will have a higher tendency to overfit, because end of the day your training data set is finite most of the time, your training data set is not increasing. So as a result, your model will overfit, and as it overfits, you don't want your model to overfit because your bias will, when it happens, your bias will be small, but you will have a very high variance in out of the sample. It will not do very well. So you have to be very careful about model fitting for adding more complex lag variable, and it is better to obtain a parsimonious small model and just stop there. Okay, so far this week that's how this much we will be discussing. Next week we will see you with a new video with a new chapter. Thank you very much. Take care.